Okay, so we've got recording. And we don't have anybody on yet. Okay. So for folks on the video and other folks, video now starts with the meeting when we start it. So it'll be just a couple of minutes while everybody comes in. We can't continue general chit chat though. Just because we're being recorded, we don't have to be silent.
That bridge. Expensive thing over there. Yeah, much big, but there's like a huge walkway connecting to Microsoft, two parts of Microsoft.
Oh, like, over here. Yeah.
It's all it's like a bike lane and like a walkway.
What is that? I haven't tried that yet.
Oh, it's pretty dope.
Yeah, it's pretty good. You don't have to wait for the light too, which is nice.
Oh, that's nice.
Yeah. that's the one benefit.
I like that.
I don't.
It's like multiple lights too without the bridge.
It's true. Yeah.
It's actually
Oh wow,
a nice upgrade.
Yeah, I saw a video of that opening and it's like, that looks interesting.
No,
Yeah.
it's actually a nice space too. They got like plants and shade and someone put some thought into it. It's not just like connection.
I just wondered about, it looks like they've got a canvas top on it.
Yeah.
And I'm like, how long is that really gonna last? I don't know.
I don't know exactly what the material is.
Yeah. But I see more and more people building stuff like that now. It's like, canvas, I always used to think, maybe 5 years, maybe 10 years type of thing.
Remind me a little bit of Denver.
I was gonna say,
Yeah.
Oh, has it got a okay.
It's got that.
Those tent-like structures.
Yeah, so Blue's got their tent, and then you can go buy yurts and stuff like that. And I've seen a couple other, buildings that, this looks like, a permanent building, right? This isn't a temporary thing. And it's got a fabric or a,
Yeah.
I don't want to say canvas because I suspect that's really not what it is, but it's got a fabric sheath on it. It's like, does that really last long enough now to justify?
It's replaceable, right? So I mean, that's the nice thing. It's 5 years. If it's nice, just get a new one.
As long as the color is maintainable enough. Yeah, I don't know exactly who maintains it. Well, I mean,
we'll come back in 5 years.
Replaceable enough.
Yeah, we'll come back in 5 years and see what the bridge looks like. If it's all like stars and stuff coming down, maybe you don't want to build with that.
That's right. And they got the closed for maintenance, and you can't use it anymore.
All right, getting a few people online. Spinning logo. I know we got a couple people in the Rust group, so coming over. So we'll wait for that.
Suggest?
Speaking of said person, how you doing?
Doing good, thanks. How are you?
Pretty good. Give people a couple more minutes to come in. What was the Rust topic today?
They haven't started it yet.
Oh, okay.
It's Rust can replace Python, really? But they were talking about other things so far, like we're going to have these topics going forward. What would beginners like to hear in our next lectures?
Oh, that's cool.
This is the news about the latest languages that are similar to Rust, that kind of stuff.
Very cool. I need to find out if they're video recording that because I need to attend this one. I'd like to attend that one too.
Right.
There's 2 other talks going on in here that I would really like to attend, and I'm one person.
Tonight they just started live streaming on YouTube for the first time, and they're
Oh, that's cool.
When they live stream on YouTube, of course, they archive.
They're going to record it.
So you should
Perfect.
be able to find it.
Oh, sweet.
And if you don't like the talk tonight, I want to be offended if you want to see it.
Well, I'm really into CUDA as well, so I am definitely trying to learn more CUDA. Although I don't have quite as much bandwidth as when I first started it.
It's interesting. There's a lot of stuff. There's actually much stuff to cover in 1 hour. So
Oh, yeah,
much we can go through today.
Yeah.
Now, if folks want, we can start the CUDA users group, but not sure we have enough interest. Okay, I think we're in pretty good shape. I guess we'll get going here. So welcome to the July Northwest C++ users group. Oh, this is interesting. This was working.
Beach ball.
And you were worried about your stuff not working. We literally just tried this.
Your message response system, maybe it's just a slides programming time.
Yeah. No, I don't know what it's doing. This literally worked a minute or so ago. When we tried it. Okay, we're just gonna go with this from memory. I'll let you get prepped. So welcome to the Northwest C++ user group July meeting. First off, want to remind everyone that we do have a code of conduct here now. It's the Microsoft Reactor Code of Conduct. So please be respectful to each other, don't hog the conversation, things like that. Second, I would like to thank Microsoft for sponsoring our Teams meeting and our meeting room, which also kind of goes along with why we follow the Microsoft Code of Conduct. The next meeting in August is going to be a pizza feed. We will not be here. We've rented a picnic shelter at Grass Lawn Park, and we're going to provide, some pizza. And basically, I'd kind of like to get a show of hands of how many people are thinking of attending. I don't remember the exact date. It's the third Thursday in August. It's like the 18th or something on that order.
Same time?
Same time. Pretty much the same time. Yeah, we actually have the picnic shelter from like 4 o'clock to 8 o'clock or something on that order. Because you just rent it for a half a day.
Mhm.
Yeah, but we'll probably do like 6:30 to 8, something like that and we won't have a presentation, but it'll just be, a chit chat social fest with pizza and pop. Because we haven't done that in a while. So how many people do you think how many people are thinking of attending? So 3, 4, 5, 6, 7, 8, 9. Okay, so we'll plan for about. Okay, just gets a ballpark. And then I would like to remind people in September, we will be back here and it will be a lightning round session. So no major presentation, but it'll just be an open forum. If you've got a 5 or 10 minute presentation you would like to do, just show up. We'll put it on the screen and we'll do that. And if we don't have enough presenters, I'll come up with some topic we can debate for a half an hour. Like, East Coast or East Cons or West Cons or where we should put curly braces. Okay, with that, I'm going to hand it over to Leonard, who's our feature presenter tonight for more CUDA.
Thank you. Yeah, it's going to be.
Plug in.
So the idea, Lloyd and I talked about doing a follow-up presentation to his last CUDA introduction. And the idea is that we want to have a bit of a progression, getting into, a bit more advanced things, although it's not going to be a super advanced presentation. Let me. So when I started putting together this presentation, I had something in mind, and as I build up the slides, I realized that I cannot go through everything in 1 hour. The planned agenda is to have a very quick rehash of the CUDA programming model, just a reminder in case, people forgot about, what Lloyd talked last month. I'm going to go through that thing pretty quickly. I don't spend too much time on it because the meaty part of the presentation is a live demo. I have an app that does something, and I'll show it in a second. And we are going to start with the basic naive implementation, and we'll try to optimize it. So the idea is to test a few changes and see what works, and then I'll do my best to explain why they work or why they don't work. And the part that I'm afraid is going to take a lot more time than I intended is having a quick tour of the CUDA toolchain. So CUDA comes with compiler for CUDA C++. It also comes with debuggers, profilers, sanitizers, and a few other things. They are very useful tools. They are pretty powerful. They are getting more and more sophisticated. So I will try to at least introduce them, name them. So if you're interested in trying them, you can at least know where to start. So I'll stick to this order, but again, I'll go very quickly over the first two parts. And if we have time at the end, we can go more in depth if we have any interesting topics to discuss about the architecture, CUDA, any particular tool or anything like that. And I will try to demonstrate some of the tools, part of the demo. It's not scripted. I didn't have a time to prepare a very scripted demo. So everything is raw. If things don't go, as planned, please be patient. So with that in mind, just a quick introduction to the CUDA architecture. What exactly is a GPU and what does it look like, especially compared to a CPU? So the first thing on the left, we have the CPU, and on the right side is the GPU. They are somewhat similar. They both have memory, they have caches, and they have compute units. But the diagram, what it's trying to show is that the CPUs, they have a small number of cores. GPUs, they have a lot of cores. That's the first major. But it is a bit more interesting than that, because it's not just the CPU with many cores. And I'm going to explain what I mean in a second. But before that, an important part of this diagram is that it helps us set up some terminology. So has anybody done any CUDA programming before? So one of the fundamental things, if you read any CUDA code or material or book or article, you're going to hear about host and device. It's really, fundamental thing. The GPUs that I'm going to talk about today, they are discrete cards. So they are not standalone computers. They are an additional accelerator. So they plug it into a PCI slot, and the host machine, the CPU, is driving pretty much all the logic, the setup and everything else, up to running the actual kernels on the GPU. So host code or host memory refers to things that run on the CPU. Memory device code is things running on the GPU. Now, the part on the right is trying to magnify a slice of the GPU. And I haven't created the diagram on the left. I don't think it's quite ideal, because the squares you see on the diagram there, they're not real cores. So the closest approximation, like trying to understand this diagram, is if you look at the rows in the diagram, that would be an SM, a streaming multiprocessor. And that's the thing that I'm picturing on the right. Because each streaming multiprocessor has its own shared memory and cache. And that's kind of like, if you look at the rows, like they all start with like a bit of the purple, and the yellow stuff is the control part. So each row would be like a streaming multiprocessor. So essentially a GPU, an NVIDIA GPU, is a set of streaming multiprocessors that look like the diagram on the right. And each streaming multiprocessor has a number of streaming processors inside, in this case, 4. So each of the thing in there, there are 4 streaming processors. And there is also, I know it's a bit hard to read here, there is an instruction cache, data cache, and the shared memory that's shared across the whole SM. And that's pretty important. I'm going to explain in a bit why that thing is important, how it works. Another thing that's interesting about the GPUs is that even though they have multiple SMs, right? So it's not just one SM, it's multiple SMs, and each SM has multiple processing units. The SMs are largely independent. So the card that I'm using on my development machine is a RTX 4070. It has, I believe, 46 stream multiprocessors. It doesn't sound very impressive when you hear that, a GPU can run thousands of threads. But each streaming multiprocessor has 4 of these streaming processors inside, and each of these streaming processors, they can run 32 threads at a time. So if you do the math, 4 times 32, that's 64, 128, right? 128 times 46 is like over 5,000 threads. So that's how many threads they can run at the same time. You can have more threads resident. So when I'm going to discuss, the programming model, you can actually have a grid of threads that's more than what you actually can execute. And there's a bit of scheduling on the GPU, but the hardware can run up to this roughly 5,000 for this particular card. Any questions so far? All right, so this is the hardware, this is the architecture. Now the programming model. So NVIDIA is using this SIMD programming model, single instruction, multiple threads. And I know that Lloyd talked about this last time. I just want to rehash things a bit.
Minor correction, SIMT's been there the whole time. I thought it came into being, it's been there the whole time.
It is for GPUs, yes. There is, so I remember I watched your presentation, I was on Teams. There is a change indeed that happened in Volta, which is one of the, it's not that recent, 5-year-old architecture from NVIDIA. There was a change in how the threads get executed. Before that, things were executed in lockstep. So you have multiple threads that kind of do the same thing, execute the same instruction in lockstep. In Volta, we introduced independent program counters. So each thread can actually run different paths, which is very powerful when you're trying to coordinate threads. If you have things running in lockstep, it's really hard to do synchronization without running into deadlocks. If you have one thread which tries to do something that another thread is waiting on, if the threads are really in lockstep, even though logically they could continue, you don't have the forward progress. And Volta introduced this. It's a very powerful addition, but it doesn't change this model fundamentally. So single instruction, multiple threads. I put it side by side with SIMD because they are somewhat similar, but there are some important differences. So SIMD, which single instruction, multiple data, you do have a type of vector processing where you have explicit instructions that operate on multiple lanes. And I'm going to have an example on the next slide. With SIMD, you have threads. Each thread has its own registers, its own local memory. And more importantly, to me, this is the biggest distinction between SIMD and SIMD is the way you program SIMD is you're writing the code for a single thread. So you don't explicitly handle multiple lanes or multiple or vector types explicitly. So the programming, how you actually program is the biggest difference. And as a final note, you can actually have SIMD within SIMD. So within NVIDIA threads, there are some instructions that are vector instructions. You can actually have some of these SIMD instructions within the SIMD threads. Just to clarify that, I have some examples. I hope they will clarify. So here's how hypothetically you would add multiple values in parallel. So on the right side, the SIMD approach, which in this case is the AVX instructions. You have a specific data type on M256, which is a set of 8 values, 8 floating point 32 values. You load them. The thing that you load has to be aligned and has a few other restrictions. You load them all, so you load 8 values at the same time. And then you add them. You have the specific instruction, this intrinsic M256 add, which adds 8 things in parallel, which gives you another of these vector types. And then you also store it the same way. So that's a hypothetical, like doing things in parallel. With SIMD, the thread gives you the position where you are within maybe a large array. So the code that you write, it's looks like a serial code. You see is A plus B. You write the code like this, but it actually is going to be executed in parallel over multiple threads. Anything else about SIMD? Like, does it make sense? Like, does it fit in with the? Okay. So I showed the architecture diagram at the beginning. That's the hardware, the one right here. Now the question is like, how does the programming model map the threads that you write to the architecture? So the programming model abstracts away a bit of the architecture. It gives you a more high-level view of the threads as a grid. So you have the grid is a set of thread blocks. All the thread blocks have the same size, and each thread block has a number of threads. All right, so let's say each block is like 32 threads, and you have multiple blocks. And within each block, the actual unit of scheduling on the hardware is a warp, which is exactly 32 threads. Currently, it might change in the future, but currently on all the NVIDIA GPUs, it's exactly 32 threads. And that is the unit of scheduling. And I'm gonna explain more as we go into concrete examples. The important thing about this logical view is that once you have a thread block, the thread block is going to be allocated to an SM. Right? So you have the hardware, you have multiple SMs on the GPU. When they actually get executed, a block will be allocated to one SM. It cannot be split across multiple SMs. And this is very important because remember, SMs are kind of independent. If you want to do things that coordinate between threads, share data between threads, or synchronize, you have to be on the same SM. And this division is not just for convenience between blocks and threads. It actually gives you a way to organize threads and knowing that within a thread block, which is also called a CTA, a cooperative thread array, you can have the threads working together. So I think this is the first part, just the introduction. Like, any questions about the CUDA programming model? The second part is the toolset. And I just want to introduce the compiler, first of all, because this is an important thing. Like, everything you do with CUDA is going to go back to this. CUDA C++ is interesting, and a lot of people believe it's very popular because it's a single source language. So you have one language. It's not exactly C++. It's a extension of C++. But it's one language where you write both your device code and your host code. So if you have an application that tries to do some processing on the GPU, you don't have to write that part in a different language. You don't have to marshal arguments across. You just write almost like you're writing, a regular piece of code. And this gives you not just the convenience, but it allows you to reuse things across host and device. If you have a structure definition like you use on the host code and on the device host code and device code, it's very convenient to be able to have a single definition of that structure and use it on both sides. It sounds like a small thing, but if you try to do GPU programming with OpenCL, for example, this becomes a bit painful. You may have differences. You may have a structure you have to define two places. If things diverge, it gets, just the ergonomics and the safety is really important. And in this particular case, CUDA C++, since it's built on C++, it gives you the full power of C++. You can use templates in device code. You can use pretty much almost anything you want. There are some limitations, but for most part, you have a single language. Now, how it's implemented, that is what I'm trying to show here. So this is the original CUDA C++ compiler implemented by NVIDIA, NVCC. There are other compilers which try to support some subset of CUDA C++, and they have a slightly different approach. But this is the official CUDA C++ compiler. And the way it works is that you start with a single source, and the NVCC compiler, it will split the host code and it's going to split the device code. And they are going to be compiled separately, and then there is a bit of magic that ties everything together. And if we have time, I can actually show you, because not only that everything here is documented, but there is a way to see the intermediate steps. You can actually see like what it generates, along this long path here. So just a quick overview of what's going on here. So the left side is the host code. So you get pretty much the host code gets pre-processed. It's going to be sent to this CUDA FE++, which is a subcomponent in MVCC, and then it's going to be passed on to a host compiler, which is another important thing. So MVCC does not compile everything, even though it's a single source. MVCC is going to compile, is going to split these two things, the host part and device code. It's going to compile and optimize device code, but the host code is actually going to be passed to a different compiler, host compiler, which can be pretty much anything. If you are on Windows, it can be MSVC. You can use Clang, you can use GCC, or any. There is a lot, there is a large set of supported compilers. And this is an important thing. If you end up doing things where the ABI or the platform has constraints in terms of compilers, this is very convenient. So it works really well with integrating with the host compilers. And on the device side, so the left side is split and passed to the host compiler. On the right side is the device code compilation, right? So it's extracted, and then NVIDIA has a full compiler that compiles the C++ code. Then it has an optimizer based on LLVM. We maintain a fork of LLVM called NVVM, and that is going to do the normal optimizations and transformations that you expect from an optimizing compiler, and it's going to produce PTX. PTX is a virtual assembly, and I'd love to talk more about that if we have time. The PTX is a virtual assembly that is not actually executable code. It has to be compiled by the driver, by the NVIDIA driver, into actual hardware instructions, which is SAS. So that's a very interesting detail. I don't know if we'll have time, but if we have time and if there's any interest, I'll talk more about that. So this is the compiler. Then I'm going to go really quickly over the other tools. I'm going to mention them, and then I'm going to try to demonstrate some of them. So for profiling, the current set of tools has a split between the system profiler, which will trace everything that happens in your system, including things that are not CUDA. So it's a full system profiler. It's called Nsight Systems. Where the profiling kind of like the boundary of the Nsight Systems stops is when you're profiling actual kernels. So to profile actual kernels that run on the GPU, you have a different profiler called Nsight Compute. It is not the best ergonomics. We used to have one unified profiler. It got sophisticated, and for many reasons, it got split into two. I'm going to show you, and you will get a feeling for how these things work. In most cases, you'll know which one you have to use. You normally start with NSI systems, you see the state of the system, and then you dig deeper with NSI compute. And NVProf and Visual Profilers, these are the old tools, and they are deprecated. So if you see any tutorials or anything mentioning them, they're not supported anymore. So you have to switch the workflow a bit. These are the profilers. There's also a set of sanitizers, which are very, very useful, since debugging on a GPU is still a bit less convenient than we're used to on the CPU. Any other tools that help you to identify issues are very welcome. And the sanitizers are pretty much the first line of defense. If something doesn't work well, I would run a sanitizer. There's a compute sanitizer command line tool, and it actually it can dispatch to multiple subtools. The ones that I listed here, there's a mem check, sync check, and init check. So again, ergonomics are not ideal. You kind of have to pick the tool that you want to run, or like go through all of them. If you don't know what's going on, you kind of have to go and run them all. But they're very powerful, very useful. And finally, for debugging, there are tools. On Linux, you have CUDA GDB, which is a GDB version that is being customized to support GPU debugging. And on Windows, you have a Visual Studio integration, which is pretty nice. And finally, you have print, which doesn't sound like much. I normally don't, encourage people to use print debugging. But just the fact that you have print working on the GPU, I think is pretty awesome, because the GPU runs on the side. Like there's nothing connected to it, right? Like the normal computer, you have, monitor, you have files you can write to. So the fact that you can write prints from the GPU is very convenient. It can be used for tracing, for many other things. Again, it's not something I would encourage people to do on the CPU, but for the GPUs is more handy than you think. So I think these are the main tools. There are more tools than these, but these are the main ones that you deal with day to day. So before switching to the last part, which I hope is the most interesting one, any questions?
I just have a short one. Going back to the sort of parallel compilers thing, if the host compiler, which you said can be MSVC or GCC or whatever, does there have to be some resolution of decisions that it made about, let's say, like alignment in order to facilitate efficient data transfer between GPU and CPU?
It's very important that the layouts match. Otherwise, things do not work. This is one of the complications on dealing with this model, the fact that you have two compilers and they have to match, and the NVCC team is trying really hard to make sure that thing is happening. It's not trivial because you have to deal with multiple compilers. Essentially, when you have to be aware of the host compiler, and you have to emulate the decisions that the host compiler is going to make. But the goal is to match, and if it doesn't, it's a bug. So
Okay, I see.
Before you go on, can you just say like a little bit how global functions fit into this, like the things you actually call, right? Like you need some amount of host code and some amount of device codes. Like how does it kind of work in here?
When you say global functions, are you talking about like __ global _?
Yeah, the ones you actually launch.
Right. So
presumably some PTX and presumably some host stuff as well.
So __ global marks kernels. It's unfortunate that the annotation says global,
Sure.
but they are kernels, and these are indeed the things you launch, right? So that's code that runs on the GPU. There are multiple ways to launch them. The triple chevron.
But I mean, in terms of where do they go in the compiler path? Do they get kind of split up and sent both ways? Does it go one side or the other?
So the device code, that's a very interesting question, because the bulk of the implementation of the kernels goes on the device side.
Mm-hmm.
And if we look on this diagram here, try to see if I can be bigger. They will get compiled, so they get compiled to PTX or to Cubin, which is SAS, is hardware instructions. eventually they get embedded in your binary, right? So you compile a thing, they're going to be embedded like as a section in your binary. How you actually launch them?
Hosts need some sort of.
So they're there, and the driver knows how to load them. But in order to launch them, you also have to set up arguments for them. There is a driver API where you can do a bit of marshalling almost manually. If you use the triple chevron syntax, which is the one I'm going to demonstrate, the most common one you see for CUDA, there's actually a piece of host stub that gets generated, which does that for you. And we can actually see, remember I said that a lot of these intermediate files actually get stored.
Yeah, you're saying.
You can actually see that. You can see the stub generated and what it looks like. So this, it's magic, but it's not a black box. You can actually pick a bit and see what's going on inside.
Okay.
Remind me and I'll be more than happy. That's a really cool thing to see, like what exactly happens underneath. So with that, let's try the demo. So what I have is an N-body, which is a pretty popular application that shows to showcase CUDA and GPU. Everything I'm going to show you here, I put it on GitHub, so you can take a look and you can play with it, find bugs or whatnot. Just a quick reminder of what N-body is, right? So you have a number of particles or bodies, and it tries to simulate all the interactions. In this case, we are going to have a 2D simulation. So, we're going to have a bunch of particles in a plane, and we start the a random initial setup, so random positions and random velocities. And then for each step, we try to do a bit of an integration, this Verlet type of integration. I have the things here, just, if somebody who's trying to follow the code, so you kind of see what's going on. If you don't follow the math, the math here is, the first one is just the gravity equation. The second thing is Newton's second law of motion. So kind of like substituting F into the second one gives you the acceleration. We're trying to compute the acceleration because what we are going to do is for each particle, we are going to look through all the other particles and compute the acceleration that are the result of the interaction between that particle and the other one. So we accumulate all the accelerations, and that's going to give us the final acceleration, and that's going to give us the new velocity and the new position for that particle. And from that description, you probably imagine that this brute force type of simulation is a quadratic algorithm, right? So you have like each particle to each one, which makes it a great showcase for GPUs, since it is easy to parallelize and is fairly inefficient if you just run it like this on a CPU, right? So the math is on the left, the pseudocode is on the right? So the idea is that we loop over each particle, and then we loop over each other particle, accumulate the acceleration, and this is going to give us the new velocity and the new position. Another thing that I try to show here is that almost all the implementations we are going to look at, they have this approach where we have two states. We have previous state and the new state that we are going to calculate. So the new state is going to be calculated based on the previous state. The reason we have two states is that it makes it really trivial to parallelize, because there are no races. Everything we read from is from the previous state, and that's immutable while we're calculating. Then we are going to swap them. So each step of the simulation is going to swap them, always read from an immutable previous state and update. And a few other things, because I'm going to show you code. We're going to use these definitions, which are hopefully they're not very surprising. We're going to have a scalar, which in this case is going to be a 32-bit floating point, something that works really well on GPUs. Vector 2 is just an X and Y, like a two-dimensional vector. And the body is, we track a position, velocity, and a mass, right? And because we have multiple implementations, I have a very simple type of plugin where you can have multiple implementations. We have this stuff on the bottom. It's an interface that can run different implementation to the simulation. So initialization is not very interesting. Rendering is something that we're not going to talk about a lot. The thing that we are going to look at is the update. Update is going to be every step of the simulation. And I think, okay, so we can start looking at the actual code. We're going to start with the CPU implementation. So what I have here.
By the way, could you please make the code a little bit larger?
I will. I will.
Thank you.
So on this stuff, let me try to fix the. If I can.
Yeah, it's like Control Plus.
Like this, right? So ideally, I would have liked to just increase the font size just for the code and not for everything else. But all right, so how about this? All right. I think we can actually get a bit more space. So the first implementation is a CPU implementation. It pretty much looks like the pseudocode, right? This is the whole code, right? So there's the render stuff is just some OpenGL stuff. It just renders a bunch of points. The update is exactly what I showed you there with a few minor tweaks. Is a 4 over the bodies, and then we have all the computation, and finally stores the final position and the velocity. And each step of the iteration, we swap the previous and the next. All right, so I have, let me see if this one is built. All right. CPU open MP. Oh, and another thing that we have here in this implementation is very basic, but we do get parallelization just thanks to this pragma. If you're not familiar with OpenMP, it's a way to get parallelization really easily. It's limited in many ways, but it's very convenient. So in this case, this pragma requests the parallelization of this loop, the outer loop, right? So we're going to get the whole thing parallelized for us. And if, all right, so we get something like this. It's unfortunately, this screen is a very high resolution. It's really small, but we don't have to look much at that one because we dumped the frame rate, and throughout this demo, we're going to look at the frames per second. It's an easy metric, and we can discuss other metrics we could use, but this one is kind of like the baseline stuff. So the default in the default simulation, we have 5,000 particles, and we get about 66 frames. So the number I'm going to look is the one in the right here, 66, 67. I can show you that we do use all the cores. So we have we have 16 cores here. That's really
You're all the cores.
So this is actually faster than my workstation, my desktop workstation. I don't have fast computers. So it's parallelized. You get a pretty decent frame rate, right? Now I'm gonna run the same thing, and I'm gonna run the CUDA version, and then so the first one is the naive, the very basic CUDA version, right? So this one gets, let's see, it's about 300 frames per second already. And
Nice galaxies forming too.
you can actually see things happening there. And once we get the faster, because this is still not quite as fast as it could be, we are going to let it run and see more interesting things happening there. Unfortunately, again, like this is a very high resolution screen. I didn't plan on a different way of presenting this, but So we get about 325. And let me write this down because actually I want to.
Put it on the board.
No, I have a spreadsheet here. So the first one is CPU open. What is the OpenMP, right? And we get well, like just roughly like 68.61. Yeah. Let's see, 68. So now we have the first CUDA one, CUDA implementation. We got. Let's take a look. See 325. After 5. Is there again 81? So I'm going to show you the CUDA version right now, so you can see what it looks like. Body CUDA. So what we have here, we have the plugin has the same structure. It's just C++ code. And this time we allocate memory that can be read from both host and the device, right? So CUDA malloc manage is a very convenient way of dealing with memory when you program CUDA, because you allocate the memory and that memory can be accessed from both exactly the same pointer. I'm going to talk more about unified memory because it's an interesting topic. But for now, the idea is that you allocate this memory, you get a pointer that you can use to read and write from both GPU and CPU host and device.
Is the MMU actually copying it, or is it the same physical memory being accessed across the PCI bus?
So it has to cross the PCI bus. Now, the way it happens with the recent GPUs, it is based on page faults, right? So the MMU.
Okay, so it's using MMU.
All the first implementations of the unified memory used to transfer memory, like when you need to like kind of like move bulk like from one side to another. But right now it's just on demand. So if you access something, it's going to be transferred. It's not already there. If you touch it, it's going to be invalidated. So if you read it from the other side, it knows that even though it had the memory there, it has to be transferred. It's very convenient, and you don't pay a huge penalty for this. There's even a way to prefetch things across if you need to. But we allocate the memory here for the bodies and prep bodies. So we have two buffers that stores these arrays. We copied them. Rendering looks exactly the same. So it's exactly the same logic. And the update, instead of having the update in here, we still do the swap trick. But what we do, we launch a kernel. And this is the triple chevron syntax for launching a kernel. Lloyd explained last time the blocks and the thread grid, right? So we pass, we have a block size and we pick the size 128, which again, it's another interesting topic in itself, how you choose the block size. And then the block count is calculated, it's a Selling division to make sure that we had enough threads to cover all the particles, right? So it's based on the bodies count and make sure that we have enough blocks to cover everything, right? And then within the triple chevrons, we pass the block count and block size. And as arguments, we pass these pointers, bodies, prep bodies, and the bodies count. The kernel code is right here on top. So what it does, it looks almost identical to the CPU code, with the exception that there is no outer loop. So the other 4 is being replaced. It's being replaced by the threads, right? So each thread is going to calculate one particle. So we have the index calculated like that. This is like the very common thing that you're going to see. In this case, it's one-dimensional. You can have two-dimensional, three-dimensional grid arrays. This is a very simple one-dimensional thing. So you have block index times block dimension plus thread index. And from now on, this is another EDM that you're going to see in CUDA. So this was not in the CPU code, right? So we calculate the index and then we have this if index is smaller than count. Does anybody know why we have that?
Yeah, Lloyd talked about last time, you get threads and blocks of 32.
So they get rounded up, right? So you may have more threads than you actually need, right? Which is important if you have if you access memory in an array or something, you don't have to go out of bounds. So this is another idiomatic thing that you're going to see in a lot of kernels. And the rest of the computation. So the other part of the computation is pretty straightforward, pretty much does the same thing, calculates all of this stuff. And if you just want to port something from the normal C++ code to run as a kernel, it's pretty straightforward. So we also get a pretty nice speed up. So let me try to inject a tool demo here, right? Because this is our first version. It's the basic CUDA implementation. It works, but let's see what the profiler says. So I'm not going to go through the NSI systems because this program is not super interesting. It just has one kernel that runs in a loop. I'll demonstrate that if we have time just to see how it looks, what it looks like. But I'm going to jump straight into NSI compute. So this is the the start page in NSI compute. What we're going to do here is just start profiling. I'm not going to go over every single detail. These tools, unfortunately, they have so many options since they do a lot of things. It can be a bit overwhelming. But if they're documented. If you have the patience and you have time, you can go through find out what's going on. So I already have this thing populated here. So you have our executable. So the basic stuff to use it is just pick an application, set the working directory, command line arguments. So nothing out of the ordinary. The interesting thing here, and this is the part that I want to double check, is you can select which metrics you track, right? And again, there's a lot of details here. I'm not even the right person to go over all of these things. But I'm going to start with the full information. So try to profile everything and see as much information as we can get and see what happens. So it starts this stuff, it profiles the kernels. We don't have to later on too much because it's essentially the same kernel. It's also very slow when it profiles, which it's something to keep in mind. But it did profile like 12 iterations, same kernels. So each row here is one iteration of the kernel. They kind of look the same, right? Which is what we expected. So we can pick any iteration and dig into the details. And now, this is a long page with a lot of things. The intention of this page is to digest and provide some actionable advice. Although it is pre-verbal, so there's a lot of stuff here. So it talks about, memory accesses. It talks about a lot of different things. Really cool stuff, very valuable. Maybe we'll look at some of these things more into depth. But I want to show you a different page, which I use more often than the summary. So I go back to the source. And here we have the preprocessed source, which but at the bottom of the preprocessed source, we have our code here, right? So this is our code. The host part doesn't have any information because it's host code, right? We are looking at the GPU. But for the kernel, we have some interesting things in here. So first of all, we have two panes. The left side is, you can select it, but normally is the CUDA code, the source code. On the right side, you can have different things. You can have PTX, which is the virtual assembly I mentioned, or you can have SAS, which is the actual ISA that runs on the GPU. The most useful stuff is, especially when you start, is to look at the source itself, right? And it has a bunch of columns here, a bunch of information. And at this point, it kind of depends on what you're looking at. I will be more than happy to go over this stuff again and look closely at some of these things. But right now, I'm just gonna remove some of these things because live registers and stuff, I don't think we have time to talk about that. I'm gonna look at this one, instructions executed. So what we see here is that we do have something that's happening here that's quite an outlier. right? So this line, is doing something. And if we look at the code, what it does, it computes the reciprocal of the square root, right? So it's not exactly surprising. Square root is not the cheapest thing to execute, but let's see if we can do something about it. So, okay, so we know that that's something that is not quite ideal. So what we have, I'm gonna keep switching between the presentation and stuff. Like, let me know if you want me to move back or. So this was the open MP implementation. The naive implementation we just looked at is again just a naive port of the CPU code. So I think I mentioned all of these things. The next version, the second version, is trying to address exactly this thing that we noticed, right? Like, let's see if we can make this faster. And there is a intrinsic exactly for this operation. It's a very common operation, and this intrinsic, not only that it does that operation, it actually, it's a bit of, I want to say cheating, but it doesn't have the same precision as the original operation. There is another instruction which you can get the reciprocal of the square root with the same precision as the original operation. Is not as fast. This one is a faster version that sacrifices some accuracy. So I'm gonna go here and I'm gonna switch to the, let's see. So the only difference between these versions is one line. So we just replaced that thing with this version, and I'm going to run it right now. So the other one was about 325 frames per second. And you know what? I'm going to switch actually because with CUDA is getting pretty fast. So I'm going to instead of 5,000, which is the default bodies, I'm going to have 25. Make it work a bit harder. So I'm going to run it first with the CUDA version that we had, so we have a baseline. So this is the 25,000 bodies, similarly the CUDA version. So we have about 81 frames per second. So I'm going to go back to the spreadsheet and we'll use this one. Instead, we'll use the 25. So 81, 71. We have to go back and remeasure it.
Really cook your laptop.
So, I mean, again, this is not a most powerful GPU either, right? It's a mobile, I think it's a RTX 3000. It's not like the most powerful or the most recent GPU either. So what we have here, so CUDA is getting ready for the. So let's run the next one, replacing the. So from 81 frames per second, let's see what we get right now. So it is a bit faster, not dramatically faster. So let's see. It hovers about 91 frames per second. I'm going to put a 92. So let's see 92 here. So this is just replacing that tiny change, improve things quite a bit. So let's see, this is the second version. The next version is a bit more involved. So what we had when we moved from the CPU to the GPU, we used exactly the same data structures. We just copied the arrays in that managed memory that can be read from both places. And the layout looks kind of like this, right? So we have the struct body. I apologize if this stuff is indeed small. So we have the struct that we use, and if we lay it in memory, it looks something like this. We have pos x, pos y of the x and y components of the velocity and the mass. They're all floating point 32, 4 bytes each. So 20 bytes per body, right? So what happens if we access them from the GPU? If you just try to access one particular body, one particular position of the current body from the, our current thread, it looks exactly like this, right? So the green bar underneath shows you what you're reading from. And obviously it works, but it's not ideal because the memory transfers, they don't work at byte or 4-byte granularity. So they work at 32-bit, 64, or 128-byte granularity. And also they have to be aligned, right? So we have these sectors or segments that are the unit of transaction with memory. So if you access the memory like this, you actually, even though you are loading two values, you are loading 32 bytes. And for the next one, you actually, you see that split in the middle. So it clearly doesn't look ideal. So one thing we can do, replace the structures that we use. So instead of having each body layout as each structure by structure, we decompose it into the components. So we are going to lay down, we're going to have a structure of array. So you have one array with just positions. And the memory is going to look like this, POSX, right? So they're all in memory. And then, the accesses are going to look a lot better for what we want. And just to be clear, this is not about cache lines, right? So there is another thing, there's data cache. The data cache is 128 bytes. But this is not about cache because you are reading things that, they're very likely not going to be in cache. This is something else. It's called memory coalescing. So because of our SIMD programming model, you have multiple threads running in parallel. And in particular, we have warps, right? We have 32 warps 32 threads that even post-volatile, in most cases, you can think as running in lockstep, same instruction. So there's an important optimization. If multiple threads from the same warp, they all do memory access, then this memory access can be combined. So instead of having, in this case, 4 memory transactions, you have a single one for these things, assuming you have a 32-bit sector here. So,
and that requires them all to be like contiguous for that?
They have to be contiguous, right? It is, the stride is important, right? So they have to be contiguous and also aligned. So there are a few requirements here. And I do have an implementation which does exactly that. So here, instead of passing arguments directly to the kernel, I have a structure that we pass to the kernel. And this structure also gives you a hint of how things are represented. So we have a vector or an array of positions. We have a vector, so one for pref positions, one for positions, one vector for velocity, and one array of for mass. And this also implements this, takes advantage of another fact that we only need the previous positions. We don't need the previous velocities. So we also get rid of having to store the previous everything. And in the init of our plugin, our implementation, so what happens, we allocate these 4 buffers and we just copy them. We copy things from the original bodies into that. And then the kernel is going to look pretty much the same, except that it's going to read from these arrays, right? From these different arrays instead of reading from a same structure. So I'm going to try right now to see if we can see any improvements with the. All right, so we got 140. Okay, so we got another nice jump. So again, it does exactly the same thing. Like the arithmetic is exactly the same. It's only the memory access patterns that are changed. And yes,
if we're accessing everything in groups of 32 bytes, do we still need the if statement to check against the count? Because if we're accessing in that chunk of memory.
So yes, we still need the check. The coalescing that happens in grouping into these segments of 32 is a hardware optimization. So you're not going to have access violation if that transaction runs over.
Sure.
So it's not a programmer's responsibility to or it is, you still have to code exactly the same as you did before. So you shouldn't run out of bounds.
Sure.
You still have to access exactly the same things.
Gotcha.
All right, so this stuff is getting faster and faster. And right now, actually, we see some interesting things happening in the simulation. Looks a bit more interesting. So let's see what we have here. 149. Let's put in the spreadsheet as
F11, yeah.
we have CUDA.
We have a half hour left too.
Okay, so I'm gonna run out of time. I'll tell you right now.
We can do another one.
All right, so let's.
This is the guy who schedules the meetings.
Where's the 19? Yeah, 19. All right, so ready to move to the next one?
Yeah.
All right, so let's see. So structure of arrays, this is pretty straightforward, but it changes the code a bit for a nice benefit. The next thing is optimizing host device memory transfer. So even though this managed memory makes it very convenient, things still have to be transferred across the PCI bus, and that is less than a tenth of the memory bandwidth. Is not ideal. Now, in this case, for this particular application, we are computing this on the GPU, and then we draw things on the GPU. So it doesn't make any sense to move things out of the GPU on the host just so you can drive the GPU again. I'm going to use something that is not really the topic of this presentation. It is a special set of APIs for CUDA and graphics interop. But I will explain what it does. So what we have right now, we have these arrays. After we did a structure of array transformation, we have 4 arrays: the velocity, mass, pref position, venue position. And the positions have to be transferred on the host for rendering. What if we keep everything on the GPU and there's something called GL array buffer. There's a buffer that you can use from CUDA and just write it there. And then when you render, the array is already in the GPU memory. So I'm just going to show you the what is this one called? What is this one is called? So we have VBO, yes. So vertex buffer object. So this one is building on top of the previous one. And hopefully it's going to be faster. So 137. To 40. So I think it's pretty much like it's not really that much faster. Oh, it is.
It is, yeah.
Okay. I lost track of these things. So 240. Okay, that is a bit nicer indeed. 40, 42. So I'm not gonna dig too much into the code because I mean I can show you the code. It's unpleasant APIs, the CUDA and OpenGL. Nothing really to look at. And so what it does, so you have to allocate a bunch of buffers, and then you have to bind them, and then you have to unbind them, map them. There are a few key APIs. This CUDA graphics register buffer. So CUDA has to know that buffer. Again, all this stuff is going to be on GitHub. Feel free to look at that stuff if you find it interesting. But I hope you get the idea, right? So we got this stuff, and I think we have one more version here, which is perhaps the most interesting thing in terms of advanced CUDA programming. So using shared memory, right? So this goes back to the thing I was talking about, the fact that you have this SM, the streaming multiprocessors, and the streaming multiprocessors, they can run a bunch of threads. They all share L1 cache, they all share the shared memory, share the instruction cache as well. And the fact that they can all use the shared memory, which happens to be very, very fast, right? So it's L1 type of memory, very, very fast. You can do some interesting things, right? So our current implementation, what it does, if you look at the grid of computation, everybody goes across everybody, right? So on the top, we have the threads, right? So each thread has one particle, and then we have a for loop that goes over all the other particles, right? So it kind of like this dark blue line is one thread, goes from top to bottom. So it has to read all the other particles, the information from all the other particles. So what we're going to do instead here is we're going to have a bunch of threads that will all, since they all have to read the vertical slice of the particles, we'll read the vertical slice just once and we put in shared memory. So we're going to have a shared memory that is going to cache a set of positions from the other particles. So we're going to load all of that stuff into shared memory, and then we do our normal thing, except that we are going to, instead of reading from memory, we're going to read all the threads in this tile. They are going to read from that shared memory. Right. So the code changes a bit. So when we iterate, we're not going to iterate one by one. We are going to iterate by tile size. So we're going to do one tile at a time. Let me show you the code, and I'm not super smart, so I don't. When I wrote this stuff the first time, it took me a while to grasp it. If you have questions, let me know. If it's not perfectly intuitive. So here's the new kernel. So the first thing we declare. So we pick a tile size we pick a tile size 128. Then we declare the shared memory, right? So we're going to have, this is how you can use, this is one way of using shared memory. You just declare a variable and then you say, okay, I want it in shared memory. So we're going to have 128 vector2 elements in this shared memory thing. Now the kernel starts very similar. So we calculate the index, that doesn't change. Our own position also doesn't change, right? So this is our own particle from our own thread. What changes here is iterating over the other particles to accumulate, and calculate the acceleration. So we are going to have, again, we're going to iterate by tile. Then the first thing we do, so all the threads in a thread block, will execute this instruction. They're going to put things in that shared memory array. Right, so each thread is going to load one element, but together they would cooperate and they would load a whole tile into this position cache array. Then we have to synchronize, because again, it's multiple threads loading things into that shared cache. We want to make sure that all the threads actually did that. They can be more than a single warp, right? So they can actually, they're not going to be in lockstep. So we have to make sure that all loaded things in the shared cache. And then we can do the next part, which is our regular computation, except that we're going to read from the position cache here. So we already have the thing there. And each thread is going to read from the same piece of shared memory. And then at the end, we have to synchronize again. And, this is an exercise for the readers, why we have to synchronize again. And finally, once we did this whole loop tile by tile, we have the final position and velocity for the particle, we store it, right? So that's exactly the same. So let's give it a try. So I think tiled maybe. All right. This one. is quite a bit faster, right? So we got another nice improvement. So let's see. $384. Well, let's say 384. It's not very scientific here, so we don't have to be super precise. So we said 384, right? 84, and let's pick one of the. So this is the last version that we're going to cover tonight. Now, I hope I convinced you that we can get things quite a bit farther from the naive implementation, right? So we started with like 81 frames per second. We got to 384 through a combination of different things. And just for the kicks, let's run the OpenMP implementation with the same number of particles. All right, so it's still, it's struggling, but it's doing something. And again, this is like, 16 cores. I mean, there's, pretty decent, right? It's 25K particles. It's not too bad. So let's see, 368. All right, so this is the last version. And at this point, depending on how much time you guys want to spend, we can go back and we can dig into multiple things. We can try some new things. I have some ideas of some of the things to demonstrate. I can show you the sanitizers. First, do you have any questions or do you have any suggestions for?
Do you have an idea how much performance is left?
That's an excellent question, right? So I don't think I can cover that tonight.
I mean, yeah, but just in this specific example.
So there is this idea of speed of light. What is the maximum theoretical thing you can get, right? And it goes on different dimensions, right? It can be memory, it can be floating point flop, right? Like gigaflops or memory. And you can also, there's something that is very popular with the GPU programming, a way to model the theoretical limit, and that is the roofline performance model. Because you pretty much have two upper bounds, right? One of them is the flops, like how much computation you can do. The other one is memory bandwidth. So wouldn't it be nice if you can put that into a picture? I was preparing to have a slide on that. I ran out of time, but since Microsoft is generous with the Wi-Fi, we can look. Let's trust Wikipedia and see what Wikipedia says. Okay, so this is a good picture. And it's called roofline because it resembles roof. So that's, and it's also, the upper bound, right? So roof in that sense. So what we have on this axis, right? On the vertical axis, you have gigaflops, right? So you can go up on gigaflops. On the right axis, you have operation intensity or compute intensity. How many floating point operations you do per memory, right? Because you load the memory, then you do something with it. So if you think about it, if you load a piece of memory and I do a lot of computation on it, right? Then the ceiling is how much computation I can do. I load a piece of memory and then I go crazy and just do like math on it. The limit is going to be the horizontal line, right? So there is an upper limit of like how much you can do. But if I read memory and I don't have a lot of operations to do on it, and I have to do some basic operations, and I have to keep loading memory to operate on them, then the limit is how much memory bandwidth I have, right? So that is the diagonal line there. It's like when I run out of memory bandwidth, right? And if you put them together, they give you an area. So this one is not really colored. Most of these things are colored and they kind of show you like what's possible. So you're like one under this roof is like what is possible. And you can have apps that were not fully like reaching the limit, that are kind of like in the middle here, right? What you want to be, you want to be somewhere like close to the upper limit, like in the corner. Ideally, you want to be kind of like there. That would be the optimal thing. Inside compute can actually estimate this utilization, so it can tell us something. I'm not the most qualified person to speak about it, but sometimes, I don't fully trust what he tells me, or maybe I don't know how to read it. So we can try that and see how, what he tells us about N-body. I think that's actually an excellent question. You can also do it analytically, right? So you can do, for example, an estimate with circle. Like this is the gigaflops I have on the GPU, and then how many operations actually I do, right? So you can multiply the number of threads, and for each thread, you can see how many operations you do, right? So for the N-body, is not that hard. You can actually look at the, let's pick up a version that's a bit simpler than the tiled one. So like VBO should be fine. So you look at the kernel and you can kind of estimate the number of operations, right? So what you have here, you have like, you have two subtractions, you have square root, the length squared is going to be two multiplications and an addition. So you have 5, so 9 square root 10. So we have 12, 15. So I count about 20 here. Okay, maybe it's not. So let's say, you have 20, you multiply that by number of threads and you say, okay, like how many operations I'm doing? Am I close to the quoted, the marketing flops, the actual, flops that you can get from the GPU, right? So that's one way of doing it. Same thing with the memory, right? So you can do it like that. And if you do this, frequently, you get better at it. You can have like, back of the envelope type of estimates. But let's see what the tool is actually telling us. So I'm going to have this laptop. I'm always using it with a different keyboard, so it's funny, completely boring right now. So exactly same exercise we did before, except that we're going to look at our best version so far, right? The tiled one. So he's going to laugh at us. He's going to say like we are like, I bet you like 20% speed of light. All right, so we have a bunch of kernels here. So let's look at one of the kernels. Okay, so throughput. Okay, so the first thing here, the first section, and let me see if I can actually magnify here. Oh, all right. Please. I guess that's the best you can do. So I don't know if I can magnify the text here. That's a bit unfortunate. Okay. So the first section here is actually the speed of light. So what it says speed of light, we are like 51% of the speed of light. The memory, we are like 15% of the speed of light. And the rest of the stuff doesn't really matter much, right? So we're not bounded by memory, bounded by compute, which is, to be honest, it's a bit unusual these days. A lot of things are going to be bounded by memory because you have so many cores doing stuff that the real limitation becomes the memory bandwidth. And that's why the GPUs, if you look at the specs, they have very fast memory. And even in this fast memory, you have, like thousands of threads running, you still run out of bandwidth for memory. So in this case, we have something that is maybe a bit unusual.
So that graph is basically saying you're using 51% of your available compute.
Right.
Okay.
Yeah. So this is the graph here. It's like tells you the same thing here. So roofline analysis. So I don't remember. It actually has a nice. I think it had a picture of the roofline. And a bunch of things here that, depending on the application, you can actually, is really cool. You can actually see, different transfers. Again, we have a very simple example, a relatively simple example here. There's another thing that is very interesting, and we cannot go too deep in today, is occupancy, which is how much do you actually fill the GPU with work. But in this case, the takeaway is that we are bounded by we barely use like half of the compute. Memory is not a problem, so we could make it faster. I mean, I don't know if we can make it 40% faster again. And obviously, as any optimization, the last
Oh, it gets harder.
it gets harder and harder to find out exactly what's going on. And this is another interesting thing that somebody told me about GPU optimization is that unless you have a very good reason, don't try to go over 80% of speed of light. So if you reach 80% with a moderate effort, it's a good place to stay. Not only because it becomes harder and harder, but the nature of the GPU is because there is so much innovation and they evolve so much in terms of the architecture. If you spend, let's see, like months trying to get like to 99%, it's not going to be portable to the next architecture because the next architecture is going to change a lot. And in order to get to speed of light, you have to use very, very specific things. You have to tweak things like the memory access, the register allocation, and everything exactly to your current GPU. And when you run it on a different GPU, you're not going to get the same benefits, right? So there are people at NVIDIA, does their job. They do that for libraries. That's why you have these libraries that, you cannot really match by hand. If you have linear algebra, you can use like cuBLAS or cuDNN and other things. Like it's really hard to match that because there are people who spend exactly that effort, and you get a new version of the library for the next architecture. But if you're writing CUDA by hand and you get to say 70, 80%, I think it's good to claim victory and move on. So the tool here is really cool. So there is also we can look at the source for the tiled version, see if there's anything obvious. I didn't actually look at this one recently. So it still, complains about the square root, which is not surprising. And let's see, registers. Yeah, I mean, at this point, you'd have to go instruction by instruction. You kind of have to look to see what's going on and see what are the things you can do. I mean, if anybody here has some ideas on other optimizations to try, I'd be more than happy to.
Well, I was curious about what you had said earlier about using SIMD within the kernels. I think that could be something to try.
That would be one thing, using, so there is, there are intrinsics to do vector loads and vector stores. That would definitely help. Now, in this case, the memory utilization is fairly low, and I don't think we are limited by that. We may not see like a huge improvement, but definitely we can do that. It's something to try. Another interesting thing, if anybody wants to play more with CUDA, is floating point 16. So NVIDIA supports floating point 16s. They are smaller, so you get the benefit of transferring less memory, and they're much faster. I don't know, like if simulation like N-body, what it, the loss of precision, like how much you did impact the simulation. But that would definitely be something to try. Yeah, and other than that, you start tweaking. Oh, another thing we can do, we can actually get. Let's do something easier. We'll do one more thing because it's really easy. So
We got 5 minutes left.
5 minutes. That's plenty of time.
Everything can be done in 5 minutes.
Talk about CUDA. It's getting easy. So, okay, let's use the big hammer.
Oh, yeah.
All right.
All right. Let's see if that's gonna. So at this point, we kind of, we.
Oh, unknown option.
What's that?
It says unknown option.
Okay. Is it underscores? Okay, let's give it another try. So you didn't complain this time, all right. So we'll try the OpenMP out. I don't remember the number.
I think it's a little more.
Good.
Maybe 50 more, something of that order.
Yeah, over 400 now.
Okay, so that's that was an easy way.
That was interesting, though.
Doing something a little different.
It is, yeah. The simulation is definitely not the same pattern we've been seeing.
Well, I mean, the start
Randomness.
state is random, but yeah. So use fast math is exactly the kind of stuff that breaks IEEE 754. You have reassociation, things that make give you different results. So when you do that, you kind of say, hey, giving up some things and get better performance. But okay, it says 420 here, so we'll take that.
Are there any ways to tell the CUDA compiler about pointer aliasing?
So you can use the same thing as you use on the CPU. You can use restrict. That's the most important thing. It'd be interesting to see if in this particular case, if that would make a difference. But yeah, that's a good point. So there's quite a lot more you can do. So how much time do we have? 5 minutes?
We have 2.5 minutes.
Okay, so I was planning to demonstrate the sanitizers, but we're not going to be able to do it in 2 minutes. I'm going to share the slides. I'm going to share all the code. And if you have any questions, you can always try to reach out.
Oh, this was awesome. Thank you.
That's an awesome talk.
And thank you.
If you'd like to do another one, just let me know.
Yeah, I mean, I could get like a real CUDA expert, which I'm not. If you guys really want to see like a CUDA wizard, that's by the side.
We're kind of joking. We were kind of joking in the back. I did CUDA without a PhD. Then we're going to do CUDA for associate degree.
Yeah.
CUDA for bachelor's degree.
Do you do something with deep learning models with NVIDIA?
Yes.
That's what it said on LinkedIn. So maybe do something like related to that.
Yes. I mean, there's a lot of interesting things in terms of a talk. Like you're talking about, like maybe.
You're allowed to.
Tell you what, we'll sync up and try to organize something else.
So part of the slides, one of the things that I did would be the best part of the slides is I added a list of references, some materials like books, articles, and also some talks. There are some really, really good talks. Stephen Jones, he's one of the CUDA architects. He has some amazing talks that goes through the physics, how the nature of physics leads to, the design of the GPUs and why things are the way they are. So take a look at these things, and there's another one about optimizing, which has maybe like a better articulated advice for optimizing CUDA code.
Hey, thank you.
Great.
Okay, folks online, we're going to get kicked out of here in about 30 seconds. So thank you for coming, and we'll see folks at the Pizza Feed next month if you could make it there.
Thank you.
Thank you. That was very good.
Yeah, thank you. That was great.